You have taken a class, right? You have taken
Yes, sir.
aspects. Have you taken a
No,
class?
sir.
No, not yet.
No, sir. Actually, I have problem with my.
Problem in your mic.
No, sir. Actually, I have migraine, so wearing specs will increase.
Okay, okay. But you should take care of your eyes, right? Very important. So, Vijit, switch on your video. Vijit, what happened to you, Vijit? You were absent for quite some time. No, yesterday you were there. You came late, probably. Vijit, are you able to hear me? Vijit?
Yes, sir. Yes, sir.
Yeah, what happened? You were quite late yesterday, and before that, I think you were absent also. So,
Sir, I
is
was.
everything, is everything okay?
Yes, sir. Okay, sir. थोड़ा बुखार
Okay.
था सर.
थोड़ा बुखार था. You should be careful, in this Corona season, right?
Yes.
Okay, so we are already late today. We'll start immediately our class. Let me check the PowerPoint. Okay. So we were talking about different types of models, numerical dynamic model versus other modeling approaches yesterday, right? And in that context, we talked about many different models, including the ICOSA hydrogen model. Okay. In today's class, as for this syllabus, I'll show you many types of atmospheric simulations, rather examples of atmospheric simulations. All right. The simulations that I will show you are basically carried out by using the dynamical models, different types of dynamical models, and this is just for like exposing you to the simulated results from complex models for different phenomena. Okay, and you can ask while I'm showing you the videos, because they are most of them are just animations. Okay, so while I am showing you the videos, because I have to open it one by one, somehow videos which are linked to my PowerPoint, they are not working properly. Okay, so I will open the videos one by one, and it might take some time, but I'll try to finish it today. Okay, so here we go about the atmospheric processes modeling. Okay, simulation and visualization. Well, this is a talk which I had prepared long ago when I was working at NCMRWF, the National Center for Medium Range Weather Forecasting. Okay, so the different atmospheric processes you already know. For example, the way the weather and climate evolves, right? The monsoon systems, the cloud processes, okay, different types of cloud that occur, the thunderstorms, okay, the cyclones, El Nino phenomena, right? Air pollution, radiation mechanisms, convection, boundary layer, okay, land surface processes, and so on, right? There are different atmospheric processes, and by using the numerical models of different types and categories, we can simulate these phenomena. Okay, we can simulate these phenomena, and in today's lecture, I'm going to show you some of them. Right? For example, what I will show you today is an example of the simulation of clouds over the Indian region during an active monsoon season. Okay, that I will show you today. The simulation of a cyclone, or they call typhoon rather, over South China Sea. Okay, over South China Sea, as you know, the cyclone is called a typhoon. So the simulation of a typhoon using a numerical model, that is MM5. I'll show you that today. Climate simulations. Okay, I'll also show you some examples of the climate simulations today. In that, I'll show you how the climate looks like when we simulate it in a controlled environment using a control model. Like we can have different numerical experiments using the model. For example, we can see the impact of increase in carbon dioxide. So I'll show you how when we introduce the carbon dioxide or increase the carbon dioxide in the model, how the simulations looks like. Okay, the effects of greenhouse gases, the effects of greenhouse gases and the aerosols, clouds and rainfall during July using a global T170 model. Well, this T170 model is a spectral model. And I shall talk about the spectral modeling later on in this subject. Then I'll show you some examples of the El Nino. Okay, El Nino. You know about the El Nino, right? Most of you must have read about the El Nino, isn't it? Are you all familiar with the El Nino phenomena? Yes or no?
Yes, sir.
Okay, yeah. So I'll show you some examples of this simulation of El Nino. A severe El Nino in 1982. Okay, El Nino versus non-El Nino year 1997. So comparison between the two as simulated by the model. Okay, and also how the OLR anomalies look like the outgoing long wave radiation. How the anomaly of the OLR looks like during the El Nino, that I'll show you. Okay, then I'll show you some of the simulations of the cloud systems during GATE. Well, GATE is a acronym. I don't know whether you have heard about this GATE. Have you heard about this GATE before? GATE, GATE. Everybody is silent.
No, sir. No, sir.
No,
No,
probably
sir.
not.
No, sir.
Yeah, GATE, maybe you have heard about the entrance of the IITs, GATE is required for admission in IIT, but that is a different GATE. This GATE is the GARP Atlantic Tropical Experiment. I'll tell you more in detail about that later on. So the cloud systems simulated during the GATE, I will show you some of the examples today. Then some examples of the tornado simulation, real tornado and the simulated tornado. Okay, and the square lines and the storms. Right? So these are the things which I want to show you today. I hope even if I'm a bit late, more than 1:30, you should have no problem. I hope. Okay, I want to finish all these things today. Is that okay? I mean, your class today is at 2:30, right? But you may have to take lunch in between. So is that okay if we continue a bit late up to 2 o'clock? Yes or no?
Sir, we have class from 2:30.
2:30, no? So if I leave you at 2 o'clock, you can have lunch. If you have not taken lunch, or if you plan to take lunch, then 2:30 you can have the class as usual. Is that okay?
Okay, sir.
Yeah. So, all right. So to start with the clouds over the Indian region during an active monsoon season. Okay. I'll just a minute. Okay. But well, before I show you the simulated results, let me show you what are the requirements. Okay, what are the requirements of such simulations? Now, the number one requirement is that we should have a good understanding of the physical processes, okay, that occur in the atmosphere. That is number one. Number two is we should have a good observations, right, of the system that we want to simulate and visualize. Okay. Number three, we should have a very good, powerful computer because such kind of simulations which I'm going to show you today require a really very, very powerful computers. Okay. And of course, it's not a one-man's job generally. Such kind of simulations which I'm going to show you is done by a team of people working on the topic, okay, and so on. So these are the requirements for such simulations and visualizations that I'm going to show you today, right? Simulations and visualizations. Okay, to start with, I'll show you how the clouds evolve over the Indian region during an active monsoon season. Okay, an animated form of that. Um, let's see. All right. Can you somehow? These videos could not be linked in the PowerPoint, so I'm separately trying to open for you. All right. So can you see this uh, screen? This is a kind of animation. Are you able to see this screen?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
What you see is the simulation of active monsoon season over the Indian region. Okay. These different colors that you are seeing. Let me also, maybe I can hold it before it moves. Okay, this is the view from different angles. If you look at India from different direction, like if you're looking at India from east or from west or from north or from south, how the monsoon would look like. This is what is shown in this animation picture. I'll try to show you frame by frame if possible. Okay. Well, let me stop it and go back. Further go back. Okay, so sorry. So what you see here is the landscape around India. Okay, that means on the northern side you see the tall mountains, right? That is the Himalayan range, and this is the Tibetan plateau. Okay, this is the Tibetan plateau that you know. Okay, and what we are seeing is the streamlines. Okay, these are the streamlines. And as you can see from the pattern of these streamlines, are you able to see the movement of the cursor? I am not able to bring out the pointer on this map. I try to bring out the pointer, it is not working. So can you see the movement of the cursor on the screen?
Yes, sir.
Yeah, okay.
Yes, sir.
Yes.
So what you see here is a streamlines around India. In the month of July, probably there was, during a active monsoon phase. Monsoon was very active at the time. And this simulation was made by a mesoscale model. Okay, mesoscale model. You know mesoscale model, right? Mesoscales, isn't it? So as you can see from this streamline patterns, there is a low pressure circulation or cyclonic circulation here on the Arabian Sea off the coast of Gujarat. And there is another low pressure area, cyclonic circulation in the headway of Bengal, two cyclonic circulation. Can you see these two cyclonic circulation clearly? Yes or
Yes,
no? Yeah, okay. So this is a typical synoptic situation of a active monsoon season, okay? And let's see how this streamline evolves with time as the model is integrated with time, how it evolves. This animation was produced by a software called this 5D. Okay. Nowadays, this 5D was a little bit old software. But nowadays, recent version is available called Vapor, and all of you will should learn about the Vapor later on, maybe in the next semester or probably this semester. I don't know because difficult to learn no offline. Like online, it is difficult to learn. You have to be present in the campus to be able to learn such kind of softwares. Because unless you come to our laboratory, the computer lab, it will not be so easy. I mean, people can learn it. I mean, you can download the things on your laptop and try to learn yourself, but it's not easy for everyone to do that way, right? So to learn these kind of softwares, you should be present in the campus, be in the labs, computer labs. So this was drawn by a software called this 5D. Okay. So let us see. Now this is the evolution of the streamline patterns. Okay, evolution of the streamline patterns, as you can see. Now what you see now are different types of clouds which have formed over the Indian region during the monsoon season. Can you see this different patches here? This patches, can you see this patches? This patches, can you see? Yes or no?
yes, sir. Yes, sir.
These patches are basically the simulated clouds. Okay, these patches are simulated clouds, and as you will see that how these clouds will grow with time. become very tall, okay, and as it grows, the cloud microphysical parameters also increase in that clouds, right? So here I let it go, and you can see that. Now you see there are some yellow patches here. Can you see the yellow patches?
Yes, sir.
Yeah.
Yes,
See,
sir.
actually,
Yes,
yellow
sir.
patches, yeah,
Yes, sir.
yeah. These yellow patches are basically the growing cloud microphysical parameters, like the growth of the ice crystals, snow, etc. As the cloud becomes deeper and deeper, and I'll show you that these yellow patches now will grow further and will become taller and taller. Okay, as the time goes. See, now you see. Can you see this tall yellow towers? Is this
Yes, sir.
yeah,
Yes, sir.
Yes, sir.
yeah, exactly. So these tall yellow towers, as you can see, are around the foothills of the Himalayas, right? Or you can say over the Indo-Gangetic plains, right? As simulated by the model. By the way, this is not the real cloud. This is not the real cloud. This is the cloud as simulated by the model. Okay. So here, these gray color clouds in the gray color, basically they are low clouds, whereas these clouds are very deep clouds, deep cumulonimbus clouds, as simulated by the models. See that our this course is modeling and simulation, or modeling of atmospheric processes, right? So at the end of this course, of course, you may not be able to do it yourself, but eventually, in your third semester or fourth semester, you should be able to do it yourself, reproduce or produce such kind of animation by simulation. Okay, so see how the clouds are evolving. Okay, now look at this. Now the view has changed. See, the map of India has turned. And this is the view of India. If you look at it from the western side, if you look at it from the, say, uh, Afghanistan, Pakistan, this is Afghanistan. Plateau, these are the Hindu Kush Himalayan range. Okay. If you look at India from Afghanistan or Pakistan side, from the western side, this is how it will look like. Okay. This is Sri Lanka, the southern peninsula of India. Okay. And these are the clouds, the same cloud that you saw in a normal direction. Now you see it how it looks like from the east and from the west. If you look at the clouds from the west, this is how it looks like. Okay, and now you will be able to see it from different directions. This is the beauty of the model. Okay, you can see it from different direction. These are all from the view from the west. Now this view is from the north. If you look at the India, you can look at India from China, for example, or we are just standing on the Tibetan plateau, somewhere you're standing on the Tibetan plateau. Then how India will look like, how the clouds will look like. This is how it is shown here in this animation. And this is the beauty of the numerical models. You can zoom it, you can visualize it in any way you want it, right? Just for the sake of understanding how the clouds form, how the clouds look like, whether the clouds which are simulated by the models are real or not, those things you can see. And we could also similarly display the real clouds, the observations which are taken from the radars, for example, or from the satellites also. We can side by side, we can display that and compare how the model simulations look like against or as compared to the observation, right? So these are the beauties of the numerical models. Okay, so this is the view from the north. You are looking at it. Now this view is from the east. This view of India is from the east. If you are looking at India from somewhere from, say, Myanmar or maybe somewhere from the Thailand eastern side, then this is how it looks like. These tall clouds will look like that. Okay, so this is really from the east how the clouds, monsoon clouds will look like. Okay, rotation. Now again back to the normal direction, back to the normal position. Same thing again getting repeated. Okay, recycle again and again. And what you see here, now this clock moving here. Are you able to see this clock moving here? Some shaft and some numbers are changing here. Are you able to see these numbers changing? Okay.
Yes, yes, sir.
Yeah, actually this number is basically showing the date. Okay, and this is the time, hour of simulation. This clock is basically set according to that. As the model is simulated with time, as the date changes, the time changes, how the the cloud patterns change. This is what is shown in this plot. Now, what you are seeing is basically a vertical cross section during an active phase of the monsoon across, say, from Afghanistan to this side, northeastern part of India, Myanmar. Okay, vertical cross section. And these colors that you are seeing, this now orange, yellow, reddish color, and this green color, etc. These colors basically are showing you the fluxes of heat, latent heat, and sensible heat. Right? How the fluxes of heat and moisture evolves with time. This is what is shown in this vertical cross section across the monsoon trough. Actually, we may be doing that in the active phase of the monsoon. The trough of the monsoon is elongated over the Indo-Gangetic plain. Okay, this is the Indo-Gangetic plain. So across the Indo-Gangetic plain, now in the monsoon trough region, how the fluxes of heat and moisture will change is what is shown in this animation. So now I'll let it go now. Okay, I'll see the changes in the fluxes. Are you able to see the changes in the fluxes? Evolution with time?
Yes, sir.
Now it change. Okay. Now next, what you see is the precipitation, the rainfall, okay, occurring over the region. Okay, and you will see soon the rainfall contours in different colors. One in the pink and some in the yellow. Okay. Now these pink and yellow colors, as you will see, or as you are seeing, are basically the different types of precipitation, like convective precipitation, non-convective precipitation. Have you heard about the convective and non-convective precipitation? Yes or no? Yes or no?
Yes, sir.
Yeah, you have heard it. Good. So you have got different types of precipitation. One is the convective, other is the non-convective, also called the large-scale precipitation. So in this animation, what you are seeing now, the evolution of the convective and non-convective precipitation. Okay. Now in the bluish contour and in the pink contour as well as in the yellow contours, different magnitudes of these things, precipitation. Okay. So this is what it is. So this is just one example. Okay, I just explained to you in detail about this, but other animation probably I will not explain so much in detail. Okay. So this is one example of the clouds over the Indian region during an active phase of the monsoon. Now this one is cyclone or typhoon over the South China Sea. Okay, now what I am going to show you is the cyclone over the South China Sea, a simulation of that using a model, a numerical model. Okay, now let me search because somehow it was not connected to the PowerPoint. You see where it is. Okay, MM5 cyclone. No. There is some problem in opening the format, so I have to open it in a different way. Open with media player. Oh, already played. So let me stop and go to the beginning. Okay. So is this screen visible to you clearly? Yes or no?
Yes, sir.
Okay.
Yes, sir.
And what you are seeing, or what I'm going to show you soon, is an animation of the simulated typhoon. Typhoon is basically cyclone over the South China Sea. And you can see the map. If you are able to recognize the geography, if you recall your geography map, and this map is the Eastern Asia, okay, East Asian map.
Yeah.
And here you can see Japan. This is the Japan island. Can you recognize this Japan island? This is Japan.
Yes, sir.
Okay.
Yes,
Yeah.
sir.
Yeah, exactly. And this side is Philippines, and then South Korea, North Korea,
South
and this
Taiwan.
is Taiwan, China, etc. Okay, so now I'll show you the simulation of the typhoon by using a model. Okay, MM5 model basically, which was the predecessor of the WRF, which is currently being used by thousands and thousands of people. Okay, so now here we go. Okay, now what you are seeing here is evolution of the cloud patterns during a typhoon. Okay, when a typhoon forms, how the cloud patterns evolve, and just rotating that from different angles. As you saw it in the India case, you saw the vision from the west, from the north, or from the east and from the south. And so also this is rotated to be able to see the vision of a simulated typhoon from different angles. Okay, and different color that you see, the white patches that you are seeing are basically the very high clouds. Okay, these white patches are very high clouds which contains mostly the frozen particles like ice, snow, etc. Okay, they are hot, and below that you can see some other colors, and they are the shaded values of the equivalent potential temperature. Okay, shaded values of the equivalent potential temperature. For example, if I just pause it for a while. Okay, if I just pause it for a while. Okay, right. So now you see these are high level clouds. They are high level clouds, and they are white in color. They are all actually containing the frozen particles, ice, snow, etc. Okay. Now, can you see the difference in the color here? Right, green, yellow, right? So these are the different other clouds, and then here you can see some lines appearing here. Can you see these lines appearing here? Right? Is it clear to you? These lines are clear to you or not? I'm trying to move my cursor here. Is my cursor visible to you? Movement of the cursor? Yes or no?
Yes, sir.
Yeah.
Yes,
Okay.
Yes,
sir.
sir.
Yeah. So these lines actually are, some of them are the lines of equivalent potential temperature. Okay, and also the streamline patterns. I will just again restart it. Okay, now you see how it is rotating, how the rotational effect is there. Okay, you know the cyclone, inside the cyclone there is a very strong rotation. Okay, rotational motion. So you can see the rotation of these isoplates. Okay, isolines. Okay, see the streamlines here. Okay, so this is the example of simulation of a typhoon using the MM5 model. Okay, so now we stop it. Okay, so this is another example. Okay, of simulation of the atmospheric processes using numerical model. Now let's take the third example. Okay, a third example, I'm going to show you some climate simulation. Okay, climate simulations of controlled climate, in which we are not going to introduce any additional things. In the experiment in which we introduce the carbon dioxide, suppose if we increase the carbon dioxide level in the atmosphere, how the climate will respond to it, that I will show you in the next two simulations. Okay. Unfortunately, I'm not able to click it from directly from here, so I have to go and search for, this is the climate control. So let me search the climate control here. Climate control. Okay, probably this one. So let me open this. Open with. Let me see. Maybe you can directly open, or I don't know. And wait. No, could not open directly. So climate control impact. Okay, once again there is some problem. Oh, this is JPEG file. I'm sorry. Climate control. See, this has happened because there is incompatibility. I could see in my office lab PC, but here it is not able to show in my laptop. Okay, so there we go. Okay, so what you are seeing is the simulation of climate using a global model for integrated for many years. See the number changing here, model year. Okay, model is integrated for about 130 years, I think 125 to 130 years. So how the climate is evolving with time. You can see this is a simulation like our more than 100 years, right? And this shaded area that you're seeing basically is the temperature. Okay, how the temperature, people are talking about the global warming, blah blah blah. Okay, so how the temperature will increase or decrease with time. That is what is shown in this simulation. Okay, this simulation is again obtained by a global climate model of NCAR. Okay, NCAR had the CCM. You might have heard about the CCM, isn't it? GCM and CCM. So this is simulated by the CCM, Community Climate Model of NCAR. And what you are seeing is basically the evolution of temperature. And these are the different years, as you can see. Year number 90, 120, I mean, moving so fast. If I just pause for a while, for example, this is 119. Year after 119 years, how this looks like everything is red here. I mean, I don't see the scale here, but everything is red. That means warming is taking place. Okay. Again, stop it here. This is after 18 years. Okay, this is 18 years, how it looks like. Okay, somewhere cold, somewhere warm, and things like that. And if I just again stop somewhere, it has changed the pattern. This is after 39 years. Okay, further, say after 63 years, a lot of warming started. Okay, this is after 113 years, and so on. Right. So this is an example of climate simulation. Okay, in a controlled way. Now I'll show you how the simulation will look like if we increase the carbon dioxide, okay, in the atmosphere. So this I'm going to stop and oops. Climate carbon dioxide increase. Okay, let me see where it is. Climate CO2 increase. Only this one. Okay. So open with already 126. I said I will take the class up to 2 o'clock today. So, oops. So, what do you see now? The changing climate when you have increased the carbon dioxide in the atmosphere. Okay, and they are again, you can see that changes with time with the year. Year 115, 1, 19, 20, 21, 23, 24, 25, 6, 7, 8, 9, 30, 31, 32, and so on. Okay, and again starting 1 million. So this is how the global climate is simulated, okay, using a coupled climate model, okay, coupled climate model, all right. So this is yet another example, and I'm going to show you the next example now quickly because a lot of examples I wanted to show you today, all of them by today itself. Now this is the climate simulation using greenhouse gases, okay, GHG, and let's see how that looks like. GHG. Yeah, this is the climate simulation using greenhouse gases. Open with. Well, now this is a different projection. What you saw earlier was a spherical projection. So this is a Mercator projection. Okay. If you introduce the greenhouse gases in the model and how the climate simulation will look like, this is what is shown in this, and here see the change in number. They are the years. Okay. How with different years by introducing carbon dioxide, how the climate will change. Okay, so this is yet another example. All right, then I will show you the next example. If you introduce both aerosols and the greenhouse gases, then how it looks like. So this is the example for that. Okay, aerosols and greenhouse gases. So if you introduce both carbon dioxide plus sulfate aerosols, okay, then how it looks like. Okay, this is yet another example, and as you can see, with change of time here, how there is a change in the pattern. Okay, so this is yet another example. All right. Then the next example is the this already we have seen. Okay, next example, the clouds rainfall during the month of July using a global spectral model. Okay, global spectral model CCM3, and let me find out where is the simulation. CCM3 TAT. I think this may be the one. CCM3 TAT. Okay, this one. Open with. So now this is again visualization in a different way. Okay, this is a Mercator projection, as you can see, right? Global Mercator projection or cylindrical projection, on which we have just animated the simulated precipitation pattern, okay, over the entire globe. And you can see, if you see carefully, sometimes you can see the vortices, how during a monsoon season, several vortex form over the ocean, and some of them they intensify into cyclone, or if they are in the Pacific region, then they form like a typhoon. They form a typhoon, right? And also the vortices they move over the land, as you know, during the post-monsoon season or the pre-monsoon season, how the cyclones move over the land and hit the populated area and so on, cause so much of damage. So what you are seeing here is basically these simulated clouds and precipitation using global T170 model. Okay, and this is July, the month of July, and this is the hour. Okay, this is the date and this is the hour. July 3 at 11th hour. Okay, and it will change. Okay, see now this is July 4, hour 21. Okay, this is July 5, July 6, hour 4, and so on. So the date and time is changing, and how with change of time and date, how the patterns also changing. Okay, this is what is shown here in this simulation, and all these things you should be able to do because students who study the atmospheric science and the sea, and also the modeling, and computing. Uh, Computer models, then you should be able to produce also such kind of simulations by yourself. Right? So this is yet another example. Okay. Then I'll show you again a different example, which is about the El Nino, right? El Nino. Okay. Let me start the El Nino. There are 2-3 examples here. Comparison of the 82 and 97. Then OLR anomaly. Let me search out these things. What is the El Nino? El Nino. Okay, SST comparison, I think this one. Okay, so right. So what you can see again, evolution of the SST, sea surface temperature. Okay, during two contrasting years, 82 and 97, 98. 82, 83, and 97, 98. 96, starting from 96. Okay, the comparison between two different El Nino years. Okay, and what you see, you know that what do you call during the El Nino season, what is the most prominent feature? Can one of you tell me? During the El Nino, what is the most prominent feature? Tell me. One of you, any one of you. What is the El Nino? What is the El Nino? Can somebody tell me? I see only 8 people are left. So who can say what is El Nino? Am I audible and visible to you? Am I audible and visible to you?
Yes, sir.
Yes, sir. Sir, El Nino, in El Nino, there is a strong heating, unusual heating of the Pacific Ocean.
Which location, which place?
So the Pacific Ocean.
Pacific Ocean में कहाँ पे? Pacific Ocean is very big area.
So in the in the tropical part.
Where location? Go more close. Where exactly?
Sir, around in the map.
Tell me where location. Where is the maximum warming? The sea surface temperature. No, it's supposed to warm, increases very much during the El Nino season. But where? Where is the maximum temperature? Maximum SST. It is now.
It is around the equator.
Equator, to ठीक है. Equator also is circumferencing the whole globe, but not over the equator. I mean, it is an equatorial belt, obviously, but The exact
Sir, in the like the part where both America, like North and South America, meet at that part.
yeah, well, not exactly at the point of meeting, but it is off the coast
Sir,
of.
around that area, like where they like lower part of the Northern America and just some part of the Southern America.
Actually, not exactly like that. It is maximum off the coast of South America. Okay, maximum SST warming takes place off the coast of South America. Okay, west coast of South America, and more precisely, it is close to Peru. Peru is the name of the country, right? You have heard of the Peru, right? Peru.
Yes, sir.
Yeah, Peru is the name of the country. So more close to Peru in the Pacific Ocean, off the coast of west coast of South America, the maximum warming occurs in the SST, sea surface temperature, and that's what you are going to see now. Okay, I just asked you to ensure that you know what is. See, you can see this is the North America, right? And this is the South America. Okay, North America, South America, and these are the SSTs. Okay, stimulated by the model. SST is stimulated by the model, and you can see the red color indicates warming. Okay, red color indicates warming, and you can see the maximum red, deep red, is somewhere here. This is South America. South America. Okay, off the coast of South America, there is a maximum warming. No, maximum red color, and this is what is called because of the El Nino. Okay, and there is a contrast between the 82 El Nino and the 97 El Nino. Okay, 97 was much more pronounced. Okay, 97 El Nino, as you can see from here, much more pronounced. And by the way, these are all stimulated from the model using the coupled climate model. Okay, similar things you can also get if you just plot the observations. If you plot the observations of the sea surface temperature around the globe, you can find out similar pattern of warming. Okay, so this is basically a proof or assertion that the models are doing quite good. Okay, models are able to simulate the evolution of the sea surface temperature properly and produces the maximum sea surface temperature of the coast of South America close to Peru. Okay, maximum SST. Okay, so this is yet another example. Okay, of this simulation. Now the next example I'm going to show you is about the OLR anomaly. Okay, OLR anomaly during the El Nino year. Okay, how it looks like OLR anomaly. Now let me see where is this OLR anomaly. SST. Okay, probably this one. OLR anomaly. Okay. Now again, the projection is different. Now this is a Mercator cylindrical projection, and different years. Okay, 82, 83, 84, 3 years simulation. Okay, and you can see the evolution of the month and year here, and you see here how it is changing. Okay, with time. The OLR. This is, mind you, this is OLR, not the SST. Okay, you know what is the relation between the OLR and the convection? What is the difference between, what is the relation between OLR and the convection? Any idea? Any idea? Everybody is silent. Huh?
No, sir.
No? Okay. So basically, there is an inverse relationship between OLR and the convection. Okay. Higher the convection, that means deeper the cloud, and lesser will be the OLR. Okay. And so when there is a El Nino year, there is a maximum warming taking place here. So most of the clouds will form here. The deep clouds, the deep convective clouds will form here. Okay. And so accordingly, the OLR will change. Okay. And this is what is shown here in this simulated OLR anomaly. This is actually an anomaly, not even direct OLR. This is an OLR anomaly. Okay, you know what is the anomaly? Right? So this is an OLR anomaly as simulated by the model, the CCM, for 3 years, 82, 83, and 84. Okay, so this is yet another example of simulation. I'll show you more examples. I'll quickly finish because I want to stop at 2 o'clock. So let's see. Now this is about the gate. Okay. Now let me tell you about the gate which I just mentioned in the beginning. Okay. The cloud systems. So cloud systems during the gate. Okay. Is this slide visible to you clearly? Why did not?
Yes.
Okay. Right. So GATE stands for GARP Atlantic Tropical Experiment. Okay. GARP Atlantic Tropical Experiment. GARP also is an acronym. GARP stands for Global Atmospheric Research Program. Okay. GARP stands for Global Atmospheric Research Program. So GATE stands for GARP Atlantic Tropical Experiment. Now this is a observational field campaign which was conducted to study the convection, the deep convection, evolution of the deep convection over the tropical Atlantic Ocean. Okay, using many types of instrumentations like ship observations, balloon observations, and whatever technology was available in those days. Mind you, when was the GATE conducted? The GATE experiment, the GATE field experiment was conducted in 1974. See, long ago. How many years ago? From today? 74 to 2000 becomes about 26 years. And after that, plus 21. 26 plus 21, kitna aaya?
47.
47, right? So this GATE experiment was conducted 47 years ago over the Atlantic Ocean, tropical Atlantic Ocean, to study the deep convection. Just imagine, in those days, not many sophisticated instruments were available. Aircrafts were used for observations, but radars were not sophisticated. Okay, satellites, it was not even the satellite era, because satellite era started after 80s, right? So even in those days, people used whatever technology was available to conduct field experiments to collect observation and study it, right? Most recently, and after that, so many experiments have been conducted, field experiments have been conducted. You might have heard about them. Like we had a MONEX. MONEX, have you heard about the MONEX? MONEX, MONEX. Yes or no?
No, sir.
No, MONEX. MONEX is a monsoon experiment. MONEX is a monsoon experiment. Monsoon experiment was conducted. Let me use the whiteboard if I can use the whiteboard. I know the time is not much and I want to finish it today. Let me see if I can write on the whiteboard. Okay. Okay. MONEX, MONEX. This is the monsoon experiment. Okay. Monsoon experiment was conducted in 1979. This is also quite old, right? Almost like 42 years ago, roughly. And MONEX was conducted over the Indian Ocean region. Okay. North Indian Ocean region, including Bay of Bengal and the Arabian Sea. And even in those days, of course, we used ships, observations, and we used the radiosonde balloons, and also whatever other technologies were available to collect observational data during different phases of the monsoon, like during the pre-onset phase of the monsoon, during the active monsoon season, during the break in monsoon season, during the depression formation, okay, formation of the monsoon depression. A lot of observations were collected. It spanned for I think May, June, July, 3 months. For 3 months continuously, the Monex was conducted. That also is quite old. After Monex, you might have heard about, I don't know whether you have heard about that or not. This was the Bob Mex. Bob Mex. Have you heard about the Bob Mex? Sometime, I think, 1999 approximately, or 1999 or 2000, something like that. Okay, Bob Mex. You know what is Bob Mex? Yes or no?
No, sir.
This is Bay of Bengal monsoon experiment. Okay, Bob Mex, Bay of Bengal monsoon experiment. And by this time, of course, we had a lot of technology because already satellites were available. No, radars were available. So we could use satellites and radars and ships observation over the Bay of Bengal and take a lot of observations. Okay, these observations are very, very important for understanding such kind of systems. Okay, both observationally as well as using the model, because we can fit these observations in the model and simulate many, many things which otherwise cannot be seen. Okay. After BobMex, we had another experiment, large scale experiment called ARMEX, ARMEX, sometime around 2002. Okay. And now you can guess now what is the ARMEX. Can you guess what is ARMEX? Yes or no?
Arabian or Arctic?
Yes, exactly. Arabian Sea monsoon experiment. Okay.
Okay.
This is the Arabian Sea monsoon experiment, which was conducted to study especially the features of the monsoon over the Arabian Sea. Okay. So these different types of many experiments were continued. The first one, Monex, this was actually an international campaign. So international. Because many countries joined in that. USA, USSR, Japan, India, and so many countries, they joined on this. But these experiments were purely Indian experiments conducted by Indian Climate Research Program. Okay. And there are many experiments conducted, field experiments conducted. These field experiments are conducted basically to understand, okay, observationally, the mechanism, the physical mechanisms that take place now in different processes. For example, a specialized experiment like most recent one, we have been trying to conduct in the STOR, STORM. And actually this was conducted approximately from 2009. Actually this was not concluded. I should not say 2009. I can say this was conducted from starting from 2006. First time, and went on to 2000 approximately 15. Initially it was over India only, but later on it was extended over the South Asian countries. And STORM is a nice acronym, by the way. It stands for Severe Thunderstorm Observation and Regional Modeling. Okay, STORM stands for Severe Thunderstorm Observation and Regional Modeling. Okay, so this was conducted purely as part of the Indian Climate Research Program by India, okay, Government of India. And later on, of course, joined by the neighboring countries like Bangladesh, Nepal, okay, Bhutan, Pakistan, Afghanistan, Sri Lanka, Maldives, and so on. All these countries, because they say that thunderstorm occurs everywhere, not only in India, but also occurs everywhere. So they wanted to join hands with India to conduct the storm field campaign, storm program. Right? We collected a lot of observations during this time, but somehow later on it was when the other countries joined this program, then it was named as SARC storm, SAARC, SARC. Have you heard of the SARC? Have you heard of the SARC?
Yes, sir.
What did the SARC stand for? What did SARC stand for?
South Asian Association for Regional Cooperation.
Yes. South Asian Association for Regional Cooperation, right? SARC and STORM. So because the South Asian countries joined hand in conducting this field experiment STORM, so we call it as SARC STORM program. And there is a very nice paper we have published for the SARC STORM program. in the Bulletin of American Meteorological Society, BAMS. If you want to study about that, you can just refer to our paper, BAMS, in 2000, I think, 14. You just search from the internet, you can find this paper and download and read it if you are interested. Okay, BAMS in 2014. Bulletin of the American Meteorological Society. This is the Bulletin of the American Meteorological Society, BAMS. Okay, so all these things I told you because there are different field experiments conducted to study atmospheric processes over the Indian region. And the first one which I was showing you earlier was basically the GATE. I was talking to you about the GATE program. And under that context, I mentioned about all these things. Okay, so GATE is the CARP Atlantic Tropical Experiment. CARP stands for the Global Atmospheric Research Program. Okay, and as I said, the CARP or the GATE was conducted basically over the equatorial Atlantic region. I can see from the map here. See the box. Can you see this box here? Yes or no? Is this box visible to you?
Yes, sir.
Yeah. So this is the box over the tropical Atlantic region where intensive observations were collected. Intensive observations were collected to understand the deep convection phenomena. And left hand side, you can see these are the positions of the ships. See, these are the positions of the ship. This is USSR, Soviet Union ship. In those days, it was Soviet Union. Ship 1, ship 2, ship 3, and so on. And you can see there are two hexagonal area. Okay, this is one outer hexagon, and this is the inner hexagon. Okay, so the American and Russian ships were placed at different strategic locations over the tropical Atlantic region to collect intensive observations about this region to study the convection. Okay, and now I'm going to show you one example of the simulation of deep clouds over the gate using those data. All right, so let me find out gate E2 MPEG gate. Okay, I think this one. Open with. See, what you are seeing is a box. Can you see this box inside which so many clouds are evolving? Okay, inside the box, clouds are evolving, and these clouds are basically the clouds which formed or developed over the tropical Atlantic during the GATE experiment, GATE field experiment. And you can see different types of clouds: some deep clouds, some shallow clouds, some tall clouds, some white patch, which is indicating frozen particles inside the cloud, red colors, which are like rainwater, liquid water, etc., etc. Okay, so these were simulated by using a very high resolution model, MM5 model. Okay, so this is an example of the simulation of the gate cloud, deep clouds during the gate. Okay, so this is yet another example. I think one or two more simulations I will show you, and then I will stop. The next simulation I'm going to show you is about the tornado. Okay, how, of course, you must have seen a real tornado in the movie, most likely. Right? There is a Hollywood movie on tornado called Twister. Have you heard about that? Twister.
Yes, sir.
Yeah, Twister movie is fully about the tornado. How the scientists they take special observations, they chase the storm. Using taking different sophisticated instrumentation and try to collect the observations during the tornado. The storm chasers, they call a storm chasers group, very much popular in USA. Storm chasers group. Okay, so you have seen the real tornado both in the movie as well as maybe on the television. But what I'm going to show you how a simulated tornado looks like. Okay, simulated tornado looks like when it is simulated by the model. And let me search soup tornado mode. Soup tornado mode. Okay, I think this one. Open with. Okay. See, the quick, rapid animation of the formation of a supercell storm, which eventually forms into a tornado. Okay, now it's a very interesting simulation. I stop the frames. Now you can see that. See, this is tall, towering cloud here. This is basically a cumulonimbus cloud, and there are other clouds also around that. See, this is also a developing phase. Congestus, cumulus congestus. We have heard the name. Okay, this is the cumulonimbus, and this is the cumulus congestus, and there are other further small clouds like cello clouds, right? And this is the anvil which forms from the top of a cumulonimbus cloud. Okay, top of a cumulus cloud, and these colors are showing different properties, different features as simulated by the model. Okay, and you can see that. See how well matured tornado, cumulonimbus supercell, and even the lightnings also seems like as if the lightnings are also occurring, as if lightnings are also occurring. Okay, so this is the animation, and this again rotation from different angles, so that you can see the tornadoes from different angles. And here you can see the streamline patterns, the wind patterns at the bottom, the red streamlines at the bottom. Okay, so this is how a tornado forms from a supercell thunderstorm. Okay, now this is a view from the top. This is a view from the top. You go above the tornado's top, then how it looks like. This is how it looks like. Okay, so this is the animation or simulation of a tornado using a numerical model. I think this was also simulated by using the MM5 model. Okay, so quickly I'll go to the next simulation because we don't have much time. Okay, this is a square line simulation, and what I'm going to show you maybe two square lines. One is the two-dimensional pattern, and other is a three-dimensional pattern. So quickly I'll try to show these things to you. Square line, okay, and this probably is a GIF file. So just I can open the GIF file. I hope. Yeah, what you are seeing here is the animation of a two-dimensional cross section of the cloud microphysical parameters in a square line. Okay, inside a square line. Okay, this is the horizontal distance, 425 kilometer, 450 kilometer, up to 600 kilometer. Okay, and these colors are showing you different cloud hydrometeors like rain, water, okay, liquid water, grapple, okay, snow, etc., etc. These colors. Okay, and this is the height. How the cloud microphysical parameters they change or evolve, okay, with time during a square line formation. This is what is shown as simulated by a model. Most likely this is simulation from the WRF model. Okay, see yet another simulation. And for the last example, I'm going to show you about WRF storm, the three-dimensional WRF storm. I hope I can find it out. Yeah, I think this one. This is also a GIF file, so no problem. Okay, so how a thunderstorm is simulated by using a WRF model. Okay, and this is trying to show you the three-dimensional pattern of the cloud hydrometeor profiles now simulated by the WRF model. Okay, so I'm going to stop this now. All right, and already almost 2 o'clock. Okay, so this is what was trying to show you, and very yeah. So examples of atmospheric simulations. Okay, this is what I have shown you. Different examples of atmospheric simulations today. All right. So today we stop the class, and tomorrow, although in the timetable there is no class shown. Okay, but I'm just thinking that we can have the class if possible. Okay, I'm going to stop sharing the screen and also stop recording. Stop recording.